Hi, everybody. Nice to see everybody here. Yep, as Mark said, I'm going to talk to you today about the Shoreline prediction system. And this is really sort of a culmination of all the data that we collect, putting it into one kind of final product when it reaches the coastline. And what you're looking at in the background here is Torrey Pines State Beach. And this is one of the locations that is on the deliverables for getting that to you by the end of the year, a prediction system there. So I just wanted to keep this in your mind, fresh in your mind. And let's see. Hold on. All right, so what I'm showing here is the kind of thing that you could expect from something like coastal flooding. This is at Imperial Beach, California. This is Cortez Avenue, which is a pretty low-lying street here, and this was a high tide, high wave event. And you can see the waves as they're rushing up the beach, over the riprap here, down into the street, and into some cases the garages behind that. And this is the kind of thing that we're working on, trying to predict and help with getting that information out there on when you might expect to see events like this happening at the coastline. And I know, Darren, you're talking about seeing the wave part and the erosion part. Yes, but small plug for the waves. They do matter. Okay, so it's estimated that by 2100, the California quote unquote flooding days are going to be occurring almost daily. And so what that means is that due to sea level rise and the tides, that the water will be elevated enough so that you could get coastal flooding. And this is under the NOAA intermediate scenario for sea level rise. You can find that at nasa.gov. And so we have a couple of photos here to remind you all of what that coastal flooding will look like. And in many cases, what you end up getting is coastal erosion against infrastructure. In one case, this is something that happened just recently in Malibu at the Point Dume access road, where the waves cut back onto this road entirely. And this is Cardiff State Beach. So in many of these cases, what happens is you need to come and have like a bulldozer push the sand out of the way and stuff. So our product is hopefully going to help people anticipate when that might need to happen. And here's an example of what happens when it's a little bit more of a nuisance type event, sort of flooding, where maybe it's limiting some car traffic and you're ending up getting a lot of water, salt water in the street. And so the idea with having this 2100 number here is to keep in mind that by the end of the century, almost every day is expected to be a flooding day. And so this nuisance flooding that's occurring here on the occasional basis is more likely to be damaging to our coastal infrastructure. And so this talk is going to go over an introduction to total shoreline water level, what we call TWL, and then go into the shoreline prediction system and how that works, and then the current products that we do have, and then the future plans on where we want to take it. So let's head back to Torrey Pines, if I can get there. All right, so this is Torrey Pines on a different day. This is now high tide. And what I want you to take notice of is that the waves are rushing up into the riprap here, but that the water level here offshore, I'm calling this ocean water level or the still water level, maybe you can't actually tell, but it is a little bit lower than the shoreline water level up here. So when I say shoreline water level, I mean what's actually the intersection of the water and the beach. And so on this day, we had waves that are about 1.5 meters, 18-second period, so it's a fairly long period, but the water up here is elevated at the shoreline. And that is because the waves are pushing up all this water up onto the beach. And so creating this elevated, what would appear to be an elevated tide. And so with that, we can get into the words of total shoreline water level. So that's a combination of a number of different factors. You have sea level rise, climatic and seasonal cycles, tides, oceanic eddies, storm surge. And then in our case here on the West Coast, what you would expect to see a lot of is the local wave effect. So that's wave run up, which is a combination of swash and setup. And the reason why we're concerned about that here on the West Coast is that because it's estimated that on the West Coast of the United States, at least, it's expected that run up and setup contribute more than 50% to the extreme total water level numbers. And the reason why that might be, as opposed to something that's happening on the East Coast, is that as opposed to getting these hurricanes that come along on our coast or on the East Coast and push storm surge up onto the coastline, here instead what we're getting is these long period swells that are coming from distant Pacific storms that are traveling across the ocean. And so you can have a nice, beautiful blue day like this and with fairly large waves and fairly large swell event and expect to see some coastal flooding. So I'm using these terms run up and set up. So now let's define what that actually means. Okay, so this is an animation of what run up and set up is at the coastline. The solid line here is the still water level. Again, that's the ocean water level offshore. And then as the waves rush up the beach, they're pushing water into the beach, which is creating this elevated shoreline water level in the mean, which is called wave setup. So the waves make the tide seem like it's slightly higher. And then on top of that, you have the swash, or what we call the wave run up sometimes. And so that's rushing up and down around the wave setup itself. And the final product of that, the highest 2% of those waves, is what we're calling the total shoreline water level. So TWL, the extreme TWL. And globally, there's a lot of operational TWL forecast systems that are out there. In Europe, you have the risk kit or the sweep owl. On the East Coast of the US and perhaps coming soon to the West Coast is the USGS total water level viewer. And then here on the West Coast, we have the CDIP flooding index. And in the Pacific, you have the PAC-IU's run up forecast. And so all of these cover broad swaths of coastline, but in doing so, they're forced to make general approximations. So perhaps you'll have one LiDAR flight, and that is the data that you have to use for what the beach looks like. And then you use one overarching formula for what the waves will be at the shoreline. And so one of the goals that we have within our group is to work on making this a little bit more precise by working at very specified locations so that we can see how to expand this into a regional sense while including all that information. So the total shoreline prediction system, in a nutshell, goes something like this. So first we have information coming from global waves and tides. That's usually from the WaveWatch 3 model. And that's putting us into regional wave models. This is run by CDIP here at Scripps. And that is validated and calibrated with the CDIP buoy network. And then those waves are then pushed into local wave models, which is the MOPS prediction system. And the MOPS prediction system gives us output of what waves look like and the general waves and current conditions and forecasts of that in 10 to 15 meters of water depth or about 30 to 45 feet. And this is happening every 100 meters in the alongshore. So everywhere that you see a little yellow dot here, that is where we can get information from the waves. And from there, when we have our waves predicted in the near shore, we can plug those into our surf zone and local observations and models. And as Adam was saying, we have collected a lot of data historically. And so we can use all that historical data to inform us of what the beach may look like at any given point in time. So we have models for what the profiles might, we're working on models for what the profiles might look like. And we have models for what the beach slope is in this location. And so from there, we can plug that into run-up models. And out of that, we can get our total shoreline prediction system. So you'll be seeing this plot a little bit later, and that is something I'm going to explain to you exactly how to read that and what that is. So let's talk a little bit about the local observations. I know that Adam has touched on a lot of the stuff that we do, but I'm going to discuss a little bit more about how it gets fed into the prediction system itself. So we use a number of different instruments to get the kind of information that we need out of this. And firstly, the major one that we have are these historical jumbo surveys. And these are collected with an ATV and a push dolly and a jet ski. And all of these are GPS equipped, and they're measuring basically the height of the sand from the shoreline or from the back beach. If I can get my mouse to go where it should, from the back beach all the way down to around the 8-meter contour here. And so we can get profiles like this every 100 meters or spaced a little bit closer or farther apart, depending on our sampling scheme. And then on the beach itself, we use tools like LiDAR or structure from motion using our drones in order to get data here on the upper beach. And from there, you can get a whole range of what the beach might look like instead of these 100-meter spaced contours or profiles. And so out of these local observations, again, we have a lot of history and data going back almost 20 years. And we can establish what it will look like to have, say, a winter beach profile instead of a summer beach profile. Again, at every single one of these points. And then we can also have our lowest observed profile, that's in this green here. So that will show you what the beach is looking like in its most eroded state of all time. And so at some locations, as I said, we have up to 20 years of subaqueous and subaerial bathymetry. And so we can really get an idea of how the beach has changed and is changing, and how it does that on a seasonal or even a more frequent time scale. And so this is an example of some of the data from a different beach, but you can see that there is a nourishment here that cut back quite a bit. So again, this will change how you would expect the waves to interact with the beach. And so getting all this data is important because the beach can change, again, quite a bit on a number of different timescales. So here's an example of what a beach might look like in the summer when it's wide and sandy. And then as we head into the winter, you'll notice that it cuts back quite a bit, and you end up with a lot of cobbles that are on the upper beach here. And notice now that there's a little bit more of a cusp-like pattern to these cobbles. And that really changes how the waves will rush up the beach. So they might not be going straight up into the beach. They might be bending a little bit around that. And it's important to understand that if we're going to be able to make any sort of predictions of what the wave run up will be. So from all that information, we can plug that into our local run-up observations and our models. And I'll give you an idea of how that system worked at Imperial Beach, coming up here on the next slide. And so at Imperial Beach, we had observations that included a seat of wave buoy and a pressure and a current meter here, as well as several pressure sensors onshore to measure whether there was actually flooding or not. And out of all of this, we were able to come up with a prediction system that looks something like this. And so on the x-axis here, we're looking at time. Each one of these is a day. each one of these labeled tick marks. And then this is the elevation above mean sea level here. So on the left-hand side, this is the hindcast of the waves, and on the right-hand side, this is the forecast. So this is heading out to about 6 days into the future. And this bottom line here is the tide and the non-tidal residual. So think of that as if we're looking at, say, a bathtub of water offshore. That's the sort of stable bathtub water. And now we have, on top of that, we have added into that the wave setup and the wave run up. So that's now you have waves and you're pushing all that water in the bathtub to one side. So this is all the water that's coming up onto the beach due to tides on top of just the regular water level. And you notice with each one of these high tide marks, we have an error bar. And the error bar is due to a number of factors, some of which include the beach slope model that we're using for when the waves rush up. Maybe the beach slope is not quite what we expected it to be. It also has error due to the wave model and the forecasts, as well as the empirical run-up formula that we're getting at this particular location. And so you notice that that error bar is actually quite wide. And one of the things and goals that we have within our group is to just see what sort of information we actually do need in order to make those error bars smaller, and what sort of information we absolutely must have if we want to get accurate predictions. So in this case at Imperial Beach, all of these flooding times were confirmed with in situ observations. That was either from a person there or a sensor. And the thresholds here in the red and the yellow are derived with in situ observations and historical accounts. So that includes newspapers and log reports and social media posts that showed that there was any sort of coastal flooding. And the moderate threshold here, we're calling something that it disrupts traffic, or there's significant sand and debris that would require a bulldozer or something to come out and get rid of it. And then the minor threshold is something like a wet street. So you will see a few overtopping events. That's where the waves rush up over the riprap. But other than that, just some sandy overwash. Okay, so in the long term, the validation of these forecast systems are very important to getting this sort of thing right. And so this is something that we are actively working on, obtaining validation for all of these sites. And at each one of these points here, now we're looking at the same plot, but we're looking at it over a longer period of time. So this is 2 months in 2 years. So this is the winter season in 2018, the winter season in 2019. And all of these little dots are when we had a confirmed flood, either from a sensor or an observer. And having that validation out there really helps to improve the accuracy of our system. And it's incredibly important for making this right. So the big question is, did we get it right? At Imperial Beach, were we able to forecast these events correctly? And in one case, in several of the cases, yes, as you previously saw, but this was a big deal with the city of Imperial Beach, and the mayor has been incredibly responsive in working with us. And it, in this case, helped the residents at least know when to put sandbags out and that kind of a thing. So we're hoping that we can use this Imperial Beach site as a framework for other sites. So having all of this information and all of this data gathered, what can we leave or what can we take from the equation in order to make these run-up predictions? So California coastal parks and beaches are also facing challenges similar to Imperial Beach. An expected sea level rise is going to increase coastal flooding, groundwater inundation, beach and cliff loss, and shoreline retreat. And effective mitigation and planning requires us to monitor and understand coastal change as it unfolds. So our goal is to establish baselines to contextualize future change. In the short term, timely high water level warnings are needed to prepare facilities. These would be the warnings here, and as well as at-risk natural and cultural resources. And then the longer term, we're working to develop observing systems and predictive tools needed to understand the coming risks and develop cost-effective adaptation strategies. I'd also like to point out that throughout all of COVID, we've still had our field team going out and collecting all of this data. There hasn't really been an interruption in any of this long-term data set collection. So that has been pretty great for the science of all of this. And over here, I've highlighted some of the new tools and ways that we are measuring things. So the way that we can improve these warnings is to include these ongoing LiDAR observations that Adam talked about, as well as remotely sensed bathymetry. And we're working to actively understand the physics, including the wave run-up, the boundary conditions, and what cobbles might do to wave run-up. And then we're trying to understand how that changes when we make approximations of the wave run-up itself. So continuing to go back in and make this an iterative process where we get validation and we go back and improve the models. And the goal is, again, if we learn on a local scale, can we apply it regionally? So we are moving this show on the road. One of the locations that we have promised is Malibu. So we do have some LiDAR data from a truck there. And then we have some more recent stuff that Adam talked about a little bit. And in these locations, we're also incorporating remotely sensed bathymetry here. And so this is an example of what you can get from a camera on a drone that's hovering in the air. Instead of using jet skis, can we get this all remotely? So if you're interested in accessing any of the data products, you can head to siocpg.ucsd.edu. And my screen has gone blank again. But here's a very sped up view of what the coastal hazard sites looks like. But if you go to the coastal processes group, you go to data products and the coastal hazard focus sites, you will be able to find the different sites that we have currently in our prediction system and scroll through and see what we have out there. So that includes beach profiles, beach width, and then we're incorporating the wave forecast as well as the flood forecast. And at the moment, we have emails that get sent out with the flood forecast at certain sites. And one of the things that we want to know from you guys is how we can better improve this product that we're trying to put out there. And with that, I am happy to take any questions.
Awesome, thank you, Julia. Any questions out there, comments?
This is Anne-Marie. This is Anne-Marie from the T1 Estuary. Really quick. We're also in Imperial Beach. Is it possible to get the wave setup animation? Because I really like it.
Oh yeah, to send you a copy?
Should I just email you?
Sure, yeah, that'd be great.
Because we're doing a teacher training in a couple of weeks, so it might be useful for that. We're doing a middle and high school teacher training.
Sure, no
Thank
problem.
you.
Yeah, I was just gonna say for parks folks, if you have, suggestions or ideas for us as far as, Julia's question about how best to get, some of the information to you, especially the prediction information, in real time, feel free to send it to myself or Nick De Silva, and we'll kind of work on compiling those comments and suggestions.
That would be great, Marina. Thank you.
And maybe just to hop in, you know, a note that I know a lot of the folks who are working in San Diego and Orange Coast, who are very interested in this data, are probably all deployed out in the field right now, or at least a lot of them are. So, you know, I do want to kind of just note that I'm sure there's a lot of voices that would have good questions, because these are the sites they work on, that unfortunately can't join us today.
This is Katrina from State Parks. I'm also discussing offline with Nick how we may be able to bring this to bear for them in their absence.
Okay, and looking ahead as we, you know, as opportunities to expand this program come into play, we're looking to include camera systems to provide that validation data that Julia was talking about, and also potentially to be able to sample the offshore bathymetry and changes in the beach that would go into a prediction system like this. So state park sites where that kind of a deployment might be really useful, we'd love to hear about.
And this is Nick. I just had a kind of follow-up question as far as kind of expanding. I know that a lot of the sites that, you know, are currently in the prediction system have extensive background data. So what does like the addition of a new site, you know, how much does that lack of background data impact the accuracy of the prediction modeling?
Yeah, and I think that's a good reason why we might want to have cameras out there, is because that helps us get the validation as to whether we're being accurate on those predictions with less information. For example, at Will Rogers, we're able to get the subaerial beach here, but all that historical data, the historical bathymetry, any of the seasonal stuff is not going to be incorporated into the product. So it's a question of whether that's good enough. We won't know until we have more serious validation there.
We are also trying to address the question of how to cost effectively get the kind of observations that we need in order to improve the site-specific model. We clearly can't get, you know, 20 years of beach profiles like we have at Imperial Beach, but with modern tools, LiDAR, remote sensing, it might be possible to gather useful validation data sets over the course of a few years at a site that is really important. That's part of the question, is how much investment do you need in order to ratchet the skill of the model up? TBD.